This lecture will cover kinetics and equilibrium. So kinetics is the study of the rates of chemical reactions. So kinetics relates to collision theory, and in collision theory, chemical reactions occur through collisions between molecules or atoms. And high energy collisions result in products forming. If you have a low energy collision, no products will form. So the factors that influence the rate of the reaction must be the same factors that affect the number of high energy collisions that occur per unit time. So we can look at the relationship between concentration and reaction rates. Generally speaking, the rate of a chemical reaction increases with increasing concentration of reactants. So, which makes sense, right? So if you have more reactants in a reaction vessel, you should have more collisions, right? And since your pressure is increasing, there should be more high energy collisions. So also, since reactants turn to products over the course of a reaction, their concentration decreases. So the rate of the reaction decreases as well over time. Temperature also affects reaction rates. So generally speaking, the rate of a chemical reaction increases with increasing temperature. So that makes sense, right? Because the temperature is related to kinetic energy. So if they have higher kinetic energy, they're moving faster, there should be more collisions and they should have higher energy. Okay, now we're going to talk about chemical equilibrium. So a reversible reaction is one that can proceed in both the forward and the reverse reaction, in both forward and reverse reactions. So for example, here we have hydrogen gas plus iodine gas makes hydrogen iodide. So you can have both hydrogen and iodine react to make hydrogen iodide, and you can also have hydrogen iodide decomposing into hydrogen gas and iodine gas. Both are occurring. And dynamic equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. So when you initially have a reaction, you're going to have all reactants and no products, right? Over time, you're going to start to make products. And eventually, your concentrations of reactants and products aren't going to change, and that's when you've hit equilibrium. Now, this doesn't mean the reactions have stopped occurring. Hydrogen gas is still reacting with iodine gas to make hydrogen iodide, but at the same rate that hydrogen iodide is decomposing into hydrogen gas and iodine gas. So your concentrations aren't changing, but your reaction is still occurring. So a particular hydrogen molecule won't necessarily stay a hydrogen molecule, but if it reacts with iodine to make hydrogen iodide, a hydrogen iodide molecule will decompose. So it's a subtle distinction to make sure that you understand, again, that when equilibrium occurs, the concentrations of reactants and products aren't changing, but the reactions are still occurring, just at equal rates. So the equilibrium constant is a measurement of the relative concentration of reactants and products at equilibrium. So if we have this reaction, AA plus BB yields CC plus DD, where the lowercase letters are molar coefficients and the uppercase letters are reactants and products, our equilibrium constant KQ is equal to the concentration of the products raised to their molar coefficients divided by the concentration of reactants raised to their molar coefficients. So it's always products over reactants. And then one thing to note is these are concentrations at equilibrium. They're not initial concentrations or concentrations before equilibrium is reached. So for example, if we have this reaction, 2N2O5 reacts to yield 4NO2 gas plus O2 gas. Our KEQ is NO2, the concentration of NO2 raised to the fourth power, times the concentration of O2, divided by the concentration of N2O5 raised to the second power. So the magnitude of KEQ tells us about the reaction. So if we have a KEQ that's much, much less than 1, our reverse reaction is favored. So that means going towards the reactants is favored. And that's because if it's much, much less than 1, this must be much bigger than this. So you have way more reactants than products. If our KQ is about 1, neither reaction is favored. So both reactions are equally favored. And that makes sense, right? Because if KQ is about 1, the concentration of reactants and products should be about the same. If KEQ is much greater than 1, the forward reaction is favored. So the reaction going this way, which also makes sense. If KEQ is much greater than 1, the concentration of products must be much bigger than the concentration of reactants. One thing to note is that we do not include solids or pure liquids in equilibrium expressions. So, for example, if we have the reaction 2 carbon monoxide gas reacts to yield carbon dioxide gas and solid carbon, our KQ is the concentration of CO2 divided by the concentration of carbon monoxide squared. We don't include the solid carbon in our equilibrium constant. So we can actually calculate equilibrium constants if we're given equilibrium concentrations. So let's look at this reaction. We have the same reaction we were looking at before. Hydrogen gas plus iodine gas reacts to yield hydrogen iodide gas. We want to know what the equilibrium constant is if the equilibrium concentrations are as followed. So hydrogen and iodide both have an equilibrium concentration of 0.11, and hydrogen iodide has an equilibrium concentration of 0.78. So first thing we need to do is figure out what our KEQ is, our equilibrium expression is. So KEQ in this case is equal to the concentration of hydrogen iodide squared divided by the concentration of hydrogen gas times iodine gas. So all we have to do is plug in our equilibrium concentrations, and we get a KQ of 5 times 10 to the 1. We can also calculate an equilibrium concentration of a given species in a reaction if we know KEQ and the equilibrium concentrations of everything else. So let's look at this reaction. If we have 2CO, F2 gas reacting to make CO2 gas and CF4 gas, and we know our KEQ is 2. We want to know what the equilibrium concentration of carbon dioxide is. If the equilibrium concentration of COF2 is 0.255 molar and the equilibrium concentration of CF4 is 0.118 molar. So again, the first thing we want to do is figure out what our KEQ is. Our KEQ in this case is equal to the concentration of carbon dioxide times the concentration of CF4 divided by the concentration of COF2 squared. So here, what we'll do is we'll rearrange our equilibrium expression. So we get the concentration of carbon dioxide, which is what we want to find out, is equal to KQ times the concentration of COF2 squared divided by CF4. We plug our values in, and we get a concentration of 0.110 molar for carbon dioxide. Okay. So Le Chatelier's principle states that when a chemical system is at equilibrium and that equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. So reactions like to be at equilibrium, so if you mess with that, it's going to do whatever it needs to do to maintain or to go back to equilibrium. So one thing that we can do is we can change concentration, right? So let's say we have this reaction, N2O4 yields 2NO2 gas. So if this is at equilibrium and then I add NO2 gas, that's increasing the concentration of my products, right? So the reaction is going to shift to the left towards the reactants to reestablish equilibrium. But if I add N2O4, the reaction is going to shift to the right to reestablish equilibrium. So you're going to make more products until equilibrium is reestablished. So one analogy I was taught when I was learning equilibrium that I think is pretty helpful is to think about a duck in a bathtub. But it's not a normal bathtub, it's a special bathtub. So you have a bathtub where instead of just having a faucet and a drain on one side of the bathtub, you have a faucet and a drain on each side of the bathtubs. So let's say you fill this bathtub up, you let the water settle, and then you put a rubber ducky in the bathtub. The rubber ducky is just going to be sitting in the middle of the bathtub, right? And this is analogous to equilibrium. If I turn on the faucet on the right side, the ducky will move to the left, away from the side that you've turned the faucet on it at. And then if you turn the faucet off, eventually the duck will move back to the middle, right? Well, this is just like adding a product. If I add a product, my reaction is going to shift away from that to reestablish equilibrium. So let's think about the duct again. So we've hit equilibrium again, and now I want to turn the faucet on the left side. So I turn the faucet on the left side, my duct will move to the right, right? And that's analogous to adding reactants to a reaction. Now let's think, if I open the drain on the right side, the duct will move towards the right, right? So that's like thinking about if I remove something, I remove a product from the reaction is going to shift towards whatever you've removed. And then again, if I open the drain on the left side of the bathtub, the duct's going to move towards the left side, and that's analogous to removing a reactant from a reaction. The reaction is going to move towards whatever you remove. Also, changes in volume can affect equilibrium. So a decrease in volume causes an increase in pressure if we're talking about gaseous reactions. So if the volume of a gaseous reaction at equilibrium changes, the pressure changes and the system shifts in a direction that minimizes the change. So decreasing the volume causes the reaction to shift in the direction that has fewer moles of gas. If I increase the volume, this causes the reaction to shift in the direction that has more moles of gas. So we look at these systems here. So I have this reaction N2 plus 3H2 yields 2 NH3. So in my reactants, I have 4 moles of gas. My products, I have 2 moles of gas. So if I decrease the volume, I've increased the pressure, so the reaction is going to shift towards the right, towards the side with fewer moles of gas particles. If I have the same reaction, but I increase the volume, which decreases the pressure of the system, my reaction is going to shift towards the left, which is towards the side with more moles of gas particles. All right, and also the temperature affects equilibrium. So if we have an exothermic reaction, remember that in an exothermic reaction, it releases heat, right? So therefore, we can write heat as a product. So if we look at the reaction that we were just looking at the previous side, so N2 plus 3H2 makes 2NH3, this is exothermic, so I can write plus heat on the product side. If I add heat, the reaction is going to shift to the left. And that makes sense, right? Just like if I added ammonia gas, my reaction shifts to the left. Well, I add heat, which is a product, so it's going to shift to the left. But if I remove heat, I cool the reaction down, it's going to shift towards the right, which makes sense. If I removed ammonia gas, right, the reaction would shift to the right. So same thing if I remove heat, shifts to the right. And then remember, endothermic reactions absorb heat, so we can write heat as a reactant. So if we're looking at this reaction, N2O4 yields 2NO2 gas, this is endothermic. So we'll write heat as a reactant. So if I add heat to this reaction, the reaction is going to shift to the right. If I remove heat, my reaction is going to shift towards the left. This is kind of a cool reaction since you can see the color change. So you can actually, I've done this reaction, it's pretty common one to do. So you can take a flask filled with this gas, and if you heat it up, it turns brown. And then if you put it in an ice bath, cool it down, it goes clear. And you can go back and forth like that. It's kind of cool. All right, so last thing we're talking about is activation energy. So here you have a reaction, right? And this is the pathway or reaction pathway, and here's energy. So if we look here, here's our reactants and here's our products. And here's the energy of reactants and energy of products. But what we have to do in order to go from reactants to products is we have to go up over this hill. We have to have enough energy to go over this hill to make products. Oops, sorry. And this energy that you need to overcome is called activation energy. If you don't have enough energy to get over this hill, this reaction is not going to occur. You can think of it like, if you have rocks, right, at the bottom of a hill. And in order to get them to the other side, you have to actually push them over the hill, right? That's the activation energy. And but you can actually lower this activation energy by using a catalyst. So a catalyst provides an alternative pathway and this lowers the activation energy barrier for the reaction. And this causes the rate of the reaction to increase. So this reaction will occur faster. And you could think about it again when we're talking about with our rocks and the hill. Well, let's say we build a tunnel through the hill, through the middle of the hill. And now we don't have to go all the way over the hill. We just have to go up a little bit and then through the tunnel, and then we'll be on the other side. It's the same kind of idea. We have a new pathway where we don't have to go up as high. And that's what catalysts do. So they lower activation energy, which increases the rate of reactions, of that particular reaction.